Hello, everyone. Well, I'm going to go through a piece that I just posted about a week ago. It's called Games Between Programs, the Ruliology of Competition. The basic setup. Whether one's dealing with biology, economics, politics, or a host of other fields, it's common to encounter situations that can be modeled as involving two agents that repeatedly compete with each other. One imagines that at each step, each agent can take one of a certain set of actions, and that then, in a kind of classic game theory way, each agent or player gets a certain fixed payoff based on the action they and their opponent take. But how do the agents decide what action to take? We imagine that each agent has a certain fixed procedure or strategy for making its decisions. And we imagine that the input to each of those decisions is the sequence of past actions that the agent and its opponent have taken. So there's been lots of work done over the course of nearly a century on particular choices of strategies. But something I've long been curious about is what happens if one systematically considers all possible strategies. And if we think of strategies as programs, this becomes a question to which we can immediately apply Ruliological methods, which is what I'm going to talk about here. Well, to be more specific about the setup, let's assume that at each step, each agent takes one of two possible actions, which we can indicate by red and green. And so let me show you that. Um, ah, hmm, it's a bug in the setup. Now, let's see. Here we go. Okay, so here's the setup. Two possible actions for each player indicated by red and green. I'm going to take the payoffs to be in what we're starting with here, to be the ones for a sort of classic match or not, or so-called matching pennies game, in which player one has the bigger payoff when there's a match between the the actions of the players, and player two gets the bigger payoff when there isn't a match. So two greens, player one gets payoff +1, a green and a red. Player two, agent two gets payoff +1, agent one gets payoff -1. So that's the setup. So what happens when agents repeatedly play this game? Well, depends on the strategies. So here are a few examples of different choices for each agent's strategy. And so what's happening here is the the choice of which action to take, red or green, is determined by the strategy that each player is using, and that it's determining that color based on previous actions that the other player used in this game. So, okay, with this setup, we can kind of plot the cumulative payoffs for the two agents in each of these five different scenarios. So we can consider the winning agent to be the one that has the numerically largest cumulative payoff, i.e., the one which is eventually on top in these plots after a certain number of steps. And with a criterion like that, we'll be able to rank different programs against each other and, in general, explore the Ruliology of competition. So, with the basic setup we're using, we can represent all possible sequences of actions by a multi-way graph. So for any given sequence of actions, there is then a cumulative payoff for each agent for the particular match or not game. So that's what's shown here is those payoffs for each of the possible paths, each of the possible sequences of actions, we get a certain payoff indicated in this way. So if each agent adopts a particular strategy, this will define a particular path through this multi-way graph. So for the strategies that we just talked about a couple of moments ago here, the paths through the multi-way graph are these ones here. So, what does it take to have a winning strategy? And what we're going to do, we'll consider strategies that are based on several different types of programs. But one basic question we can always ask is whether what turn out to be the winning strategies tend to be based on programs that are more complicated or less so, or show behavior that is more complicated or less so. So in other words, if you want to win, should you typically be trying to build up something complicated, or should you instead expect to be able to find some sort of simple hack that will crack the game and at least usually let you win? In effect, we're asking whether competition leads to complexity or simplicity. So I've recently looked quite a bit at minimal models of both biological evolution and machine learning, in which one is adaptively evolving programs in order to maximize some externally imposed fitness function. What I've found is that even when the fitness function one uses is simple, the behavior of the programs that maximize it is normally quite complex. In other words, adaptive evolution will tend to make even a simple fixed objective be achieved in a complicated way. So what if instead of having a fixed, externally imposed objective, our goal is just broadly to win against other agents? Does such potentially open-ended competition lead us to more complex behavior or more complex programs or not? That's the kind of question we're going to be able to explore here by looking at the Ruliology of competition. Strategies from finite state machines. Finite state machines can be thought of as defining extremely simple programs that might model pathways in biology, decision processes in economics, and so on. And to start our investigation of the Ruliology of competition, we're going to look at strategies defined by finite state machines. So a typical example of a finite state machine here with 3 states is this. And we're going to use this finite state machine to define a strategy for an agent. So to see how this works, let's say that the sequence of actions taken by the agent's opponent have been the sequence here. The idea is to use this sequence of actions to define a path in that finite state graph, and then to determine the next action from the color of the state one reaches in that graph. So we start at the vertex, it says with the incoming arrow, but actually it's the one with the purple circle around it. Then successively follow the edge whose color matches the next move made by the opponent. So these are the opponent's moves, green, red, green, etc. And then what we're doing is we're following the edge that matches that color. And then at the end, we'll reach some vertex in this graph, in the graph for the finite state machine. So in the particular case we're showing here, we eventually reach a red node in the finite state machine. And then the setup is that we'll say that the output of the strategy, of this finite state machine strategy, i.e. the next action for this agent to take, should be the red action. Okay, so we're using the finite state machine to read in what the opponent did, and from that to decide what we're going to do. So it's sometimes convenient to show the states of the finite state machine arranged in a line like this, and then we can kind of summarize the path taken with a certain input by showing which states of the finite state machine are visited based on that input. Okay, so what happens if 2 finite state machines compete? The basic idea is that the successive outputs from one machine become the successive inputs to the other, and vice versa. So if our second machine is this, and our first machine is the one I just showed, then we can represent the behavior of the 2 machines in something like this, where the dots are showing the succession of states that we're visiting, and the center 2 columns show the actions that are taken on the basis of those machines. So if the payoffs we use are for the match or not game, then the cumulative values for these machines turn out to be this. So in the end, what we discover is that machine 2, agent 2, can be considered the winner. So that's kind of saying that it's more often the case that there's a mismatch than a match between the colors here, based on these strategies. So it's important to note that in the setup we're using, everything is deterministic. At every step, each agent takes an action that is deterministically computed using its strategy from the past history of moves. It's a different setup from what's most often studied, for example, in game theory, where each move is in effect considered independently, but where there can be probabilities for different actions, mixed strategies, and where, in the end, averaging is done over different possible rolls of the dice. Okay, let's talk about the space of possible finite state machines. The number of possible graphs for finite state machines with S states is 2 to the S squared, all to the power S. But some of those graphs correspond to machines with identical behavior, so that the actual number of distinct machines is considerably smaller. So with two-state machines, there are 22 distinct machines, and here are those machines. And we can identify each machine by a number. And so now what happens if pairs of these machines compete? So here are a few examples of pairs of two-state finite state machines competing with each other, where in each case we're identifying the average payoff, and we can the numbers at the bottom there are the average payoff over 10 rounds of the game. So for example, in that very first case, we're always getting alternating actions, green, red, green, and so on. And that means player 2 is always getting a +1 payoff, player 1 is getting a -1 payoff, and so on. And in the second case, the average payoff for each player is 0 in both cases. So in all competitions between pairs of finite state machines, which what these are, the sequence of moves ultimately has to become periodic, with a period equal at most to the product of the number of states in each machine, so in this case 4. Okay, so what happens if each of the 22 distinct two-state machines competes against each of the other ones? So we can summarize the results by showing the mean long-term payoff for every pair of machines. So the payoff is for each machine playing as agent 1 in match or not, and the payoff is negated if it's playing as agent 2. So we've got two different pictures here. This is the payoff for playing as agent 1 with this payoff setup. So we can ask, okay, well, those are our different possible. That's very strange. That y-axis is labeled wrong. It should say finite state machine rule. I think, unless this is the wrong picture. I think this is the wrong picture. I think this slide is the wrong one. That's embarrassing. Anyway, the actual picture looks very similar to this. So the question is, what machine is the overall winner? So this picture shows the payoff for every machine playing every other machine, but which one is the overall winner? So one way to assess that is to look at the average of the mean payoffs achieved by a given machine when competing with all other distinct machines. So this is for every possible machine playing as agent 1. This is what the average mean payoff for that machine playing against all other machines. So by that measure, the winner is the machine indicated by purple here. It's machine 26, and this is what that machine is. So running this machine against all distinct two-state machines, we get the following mean payoffs. And this machine, as I say, has the highest average mean payoff. So we take all these mean payoffs for that machine competing against every other machine. We take the average of all of these and we ask what that is. And what we were showing is the average of all those is highest for this machine competing against all others than for any other machine competing against all others. Okay, so the actual behavior for this winning machine here is the actual behavior doesn't depend on the payoffs, only on the machines involved. That's what the actual behavior looks like with that machine competing with all other of the 22 minimal distinct two-state machines. The numbers at the bottom are the payoffs that we get, the mean payoffs that we get based on the match or not payoffs. So, okay, so that's what the winning machine does in this case. So what are the runners up to the winning machine? So here are all the distinct machines actually ranked by mean payoff. I'm surprised that these aren't nicely lined up. I don't know how that happened. But in any case, those are all the machines. So the winning machine is first there with the highest average mean payoff, going down to the loser machine at the end, which has the lowest average mean payoff. So if we look at the top three runners up, that's machines 2 through 4 here, here's what we get playing those machines against all other machines in this group. So we can sort of summarize how a machine behaves by showing the history of its behavior when playing against all other machines, or in effect, by putting together the first columns in pictures like the one I showed you of machine against machine above. So let's see, here are the results so what we've got here is every column in every picture here is the result of playing the particular machine that you're seeing here against each of the 22 other possible machines. So that's kind of showing, it gives some sense of the complexity of sort of the behavior that you get playing each of these machines against all other machines. So some of these machines, like the very first one, the behavior is trivial, it's green everywhere, and other ones, the behavior is more complicated. So these machines are ranked by from the highest average score down. Okay, again, it's worth mentioning that these machines are completely determined just from the machines themselves. The payoffs in the match or not game just determine their ordering on this page. Okay, so one footnote to what we've been saying here, and actually I'm a little bit surprised that that green one is the top one listed here, but I guess that's right. One footnote to what we've been saying has to do with how many steps of competition we're getting the machines to do. Because as I showed before, sometimes the one machine will win for a while and then another machine will catch up and so on. So for all finite state machines, as I mentioned, the behavior must eventually become periodic. And for two-state machines, the maximum period is 4 steps with a maximum transient of 3 steps. But the actual average mean payoffs vary with the number of steps that one considers. So that's as a function of the number of steps for each of the different machines shown on the right. This is showing how the average mean payoff changes with the number of steps one's doing the average over. So it's notable, at least for the first few steps, the rankings move around. These are the top ranked, and again, I don't know why they're not lined up properly. These are the top ranked rules for the first based on averaging over the first of a sequence of steps. And we see that the top ranked machine kind of moves around to different places. But in this particular case, it doesn't take too many steps for the ultimate winner to be clear. I mean, later on, we'll see examples. We're seeing the ultimate winner coming out at the top there. Later on, we'll see examples where it takes much longer. Well, there are all kinds of subtleties in looking at this. One of the subtleties is that we're computing average payoffs by playing every machine against every other distinct machine. In principle, we could also include other machines that have different graphs, but they're ultimately equivalent, which would slightly change the weighting of our averages. But since we're really concerned with strategies, not machines as such, the scheme we're using kind of seems more appropriate. All right, let's talk about three-state finite state machines. So there are 496 distinct machines with three states, and the corresponding kind of competitive array after 1,000 steps, showing the payoff for agent one is this. So the average mean payoff for each of the machines, i.e., the average across each row in this competitive array, is then shown here. So this is playing each specified machine against all other possible machines, this is showing the average mean payoff in doing that. So you could ask, well, what's the distribution of average mean payoffs? This is what it looks like. Not a very simple distribution, and it kind of has there's a losing machine down at -4 average mean payoff, and symmetrically there's a winning machine up there at about 0.4 average mean payoff. So if we're using the match or not game to determine our payoffs, the top few machines are then these ones here. So running these top machines, well, actually running just the very top machine, which happens to be the three-state machine 1164, against all distinct three-state machines, we get the following mean payoffs. So that's now running that particular machine, 1164, against all possible competing machines and showing the specific mean payoff after some number of steps for that competition. And the distribution of average mean payoffs here looks like this. So average mean payoff 1 is the most common, and -1 is considerably less common, and so on. So the most common forms of behavior seen with this three-state winning machine are these here. So the maximum possible period for a competition between two three-state machines is 9. Machine 1164 never quite achieves that. Its maximum period of 7 occurs when competing with particular machines, which both give limiting mean payoff -1. And those are the competitions between those are the maximum period cases of competition between two three-state machines. So if one looks at all possible pairs of three-state machines, there turn out to be 792 that yield period 9 behavior. So some examples of that are these here. So these are, in a sense, the most complicated behaviors that we can get with three-state machines competing with three-state machines. And these particular ones have no transient. The maximum transient for any three-state machine turns out to be 8. Okay, let's go into one aside. What do we mean by average? So we've talked about how a machine does on average when competing with other distinct machines. But what do we mean by on average? So far, we've taken the average to be the mean of the payoffs obtained by competing with each other machine. And the payoffs here are themselves means across successive steps. But what if we use the median instead of the mean? Well, here are the median payoffs from running each machine for 1,000 steps against all all other machines. No, this is yes, that's right. Yes, this is the median payoff. Each uh, each point along the x-axis is a particular machine that's being run against all other possible machines, and the median of the results got is what's plotted there. So there's a standout winning machine, which is machine 1172, this machine here. And in this particular case, the mean payoffs and their distributions are these here. And the median is sort of anomalously high because with this machine, exactly half of all mean payoffs are +1. So the corresponding mean is pulled down by the left tail in the distribution of these mean payoffs. Okay, let's talk about the complexity of winning. Let's look, basically as we did before, at the actual behavior of each of the distinct two-state finite state machines when competing against all other two-state machines, ordered from the smallest average mean payoff to the largest average mean payoff. So the cases with 0 average mean payoff look simple in their behavior. You can see that's just all green, all red, stripes, and so on. But for other average mean payoffs, the behavior of a given machine competing against all others seems more complicated. We can get some sense of this complexity by looking at the compressed size, as obtained, for example, from the Wolfram language function compress, of the array of behavior that we're showing here. So that's kind of plotting the compressed size, which is sort of a proxy for the complexity of behavior against the average mean payoff that's achieved. So if we look at the corresponding result for not for two-state machines, but for the 956 distinct three-state machines, this is the plot of compressed size of behavior, roughly complexity of behavior against average mean payoff. And there's no strong correlation here between the average mean payoff and our estimate based on compression size of the complexity of behavior. And if one looks at machines with the highest average mean payoff, there's still quite a diversity of levels of complexity in behavior. These are the ones with the highest average mean payoff. They're certainly not all the same kind of compressed size. So if we look at sort of the behavior traces of these machines, that's what they look like. That's one machine competing, this one winning machine competing against all other possible three-state machines. There's another example of that. So in other words, at least in this case, we really can't say that winning machines are characterized either by being particularly complex in their behavior or particularly simple. It seems that it's the detailed structure rather than overall features that determines which machines will win. All right, let's talk about competitions between machines of different sizes. Can finite state machines with more states systematically do better, i.e. achieve larger payoffs than ones with fewer states? The best average mean payoff for any two-state machine can achieve when competing with all other two-state machines is about 0.151. But for example, if we consider three-state machines competing, say, for 1,000 rounds against two-state machines, the best average mean payoff is instead 0.593. So it goes from 0.151 when we're just using two-state machines to 0.593 if we allow three-state machines. And there's a table. So if we look at the distribution of possible average mean payoffs, we see that the distribution of average mean payoffs is wider for three-state machines than for two-state ones. A fact that's at least partly just a consequence of there being so that these are now the distributions of average mean payoffs for different machines of different sizes competing with each other. So part of the reason that the distributions are wider when you have more states. It's just there are more possible higher state machines than lower state machines. But something that's notable is that the very broadest distribution is for three-state machines competing against two-state ones. In effect, it seems that with their larger collection of possible strategies, the three-state machines can do better at outmaneuvering the two-state ones. So the three-state machine that does the best overall against two-state machines is machine 1, 2, 3, 4, turns out. It doesn't always definitively win with payoff +1, but it does manage to win the majority of the time, as you can see here. So we're seeing the mean payoff achieved by that machine, the three-state machine, competing with all possible two-state machines. Most of the time, it's coming out a +1 winner, so to speak. So how does this machine achieve this? Basically, for lots of different two-state machines, this particular three-state machine manages to behave just as they do. So in some sense, there are facets of the three-state machine that resonate with many two-state machines. So we can kind of see that happening in these cases here. The three-state machine is kind of getting it's syncing with the two-state machine that it has been presented with as an opponent, and then it's able to do a good job of winning against it by kind of imitating it. So how about four-state machines? The four-state machine that does the best overall against two-state machines is this one here, 109828. Out of the 22 two-state machines, it only gets less than payoff +1 in 6 cases. So almost all the time, that four-state machine is just a slam dunk winner against all two-state machines. So here's the actual behavior from that machine in the 22 possible cases of minimal two-state machines. And once again, we can kind of think of the four-state machine as successfully covering most of the two-state behaviors. So we can kind of, this is what it's doing, and you see it's kind of winning with a +1 payoff, mean payoff, by sort of covering and imitating the two-state behaviors. All right, let's talk about adaptive evolution of finite state machines. So in many practical situations where there's competition, there's a way for the agents that are competing to evolve. So can we make a minimal model of this using finite state machines? In what we've talked about so far, we've always been looking at a space of all possible finite state machines, but what about sequences of machines found by adaptive evolution? Is there, for example, a way to adaptively evolve machines to do progressively better in competitions? So the first step in doing this is to see how we might make successive mutations in finite state machines. So a simple approach is to say that for any given mutation, any given mutation can affect either a random vertex or a random edge in the graph of a machine. So for a vertex, the mutation just reverses its color. For an edge, it either reverses the color or reroutes the edge to a different vertex, with the constraint that doing so does not disconnect the graph. So applying a sequence of such mutations at random gives, for example, this sequence of finite state machines. Or with a different graph rendering, those are the same sequence of finite state machines. So notice that we're mutating machines in whatever form we find them. We're not worrying about equivalences between machines or the canonicalization of machines. So imagine we have an opponent machine, like three-state machine 1165, that usually forces a lose, i.e. limiting payoff -1. For example, about half the time when competing with other three-state machines. So that's the machine, that's 1165. It's usually the big winner. Now we can ask whether we can adaptively evolve a machine that will win against this machine. So in order to give our adaptive evolution process some room to maneuver, we'll use a four-state machine. We'll start with a random such machine, say this one here, which loses, having payoff -1, against that machine 1165 here. So this machine is the random one we're going to start with. It's a four-state machine, and it always loses against our sort of prize opponent. Okay, and we can see it losing in this particular case. So to do adaptive evolution, we now make successive random mutations to this four-state challenger to our winning machine. So we accept a mutation if it doesn't decrease the mean payoff for that machine, otherwise we reject it. And the result is kind of a typical fitness curve in which most mutations, indicated by red dots here, don't lead to improvement in the payoff, which is what's plotted. But there are some that lead to breakthroughs where the payoff jumps up, sometimes only by a small amount, with the payoff eventually reaching the maximum value of +1. So the various breakthroughs progressively converge on a perfect solution with payoff +1. That's the sequence of evolution steps, with successive finite state machines being the results of that evolution. So concatenating the successive results over the course of the adaptive evolution process, we can see sort of the eventual convergence to a perfect solution where the actions of the two agents always match. So with different random mutations, the fitness curve will be different in detail, though will have the same general form, and the same is true with different specific opponents. By the way, using our way of numbering finite state machines, we can make a plot of how the process of adaptive evolution moves the machine around in rule space. So we're seeing which rule is the candidate plotted on the y-axis against mutation step here. But what happens if we do as we've done before and ask about the mean payoff averaged over all possible finite state machine opponents of a given size? So right now, we're looking at the payoff competing with a particular machine, 1165. Okay, so for example, how well can four-state machines do against all possible two-state machines? So starting with the same random four-state machine as before, a typical fitness curve looks like this. The fitness increases, but never reaches +1. The behavior of successive breakthrough machines playing against all size 2 machines is here. And we can see that even the best machine we get still loses to some of the two-state machines. We can see that in those plots on the right. If it was winning, it would always be in the +1 position, but sometimes it isn't. And in the end, the average mean payoff is about 0.62, whereas in the past, competing with, if we look at it, running against just a single two-state finite state machine that was our champion, we can get payoff 1. Here, asking to run against all the possible competing finite state machines with two states, the average mean payoff there is 0.62. So what happens if we look at machines that have more states? So with 10 states, for example, it's possible to adaptively evolve to a machine that achieves limiting payoff +1 against every single two-state machine. So what does the winning machine look like? Here it is. It's a little hard to understand, but it can be thought of as a kind of two-state universal winner that ultimately wins against all two-state machines. Here's the traces it makes. So how does it do it? In some sense, the machine is big enough, and what we saw back there, the machine is big enough that it can have different specialized parts for different opponents. And if we look at how the machine behaves, we do indeed see that for different opponents, the machine settles into different subsets of its complete space of possible states. The 10 states are shown in the successive columns over on the left there, where we're looking at how the machine moves between its states. So even if we consider all 956 three-state machines as opponents, our machine continues to do well. It doesn't win in all cases, but it still achieves an average mean payoff of +0.603. So some examples when the machine doesn't win, in effect, because it can't contain as much as a submachine, something to deal with a particular opponent. So some examples where it doesn't win are ones like this. So far we've considered the adaptive evolution of a single machine competing either against a single fixed opponent or against a collection of fixed opponents. But what if both the machine and its opponent are undergoing adaptive evolution? For example, let's say that on alternating adaptive evolution steps, we do a mutation on a machine and on its opponent. We keep the mutation for each machine if the mean payoff for that machine does not decrease, otherwise we reject it. So with this setup, here's the evolution of mean payoffs for two initially identical four-state machines. There are periods where one machine wins, periods where its opponent wins, as it's visible in the actual successive behaviors of the machines. So the actual machines found by adaptive evolution move around in the space again, soon kind of losing their memory of where they initially were. Those are the two machines kind of chasing themselves around in rule space. So not much changes if the number of states in the machines changes or aren't the same, though there's typically less alternation of winners for machines with more states, presumably because each individual mutation tends to have less effect on the behavior if there are more states. Okay, what about prisoner's dilemma? So everything we talked about so far has been based on the particularly simple game of match or not, otherwise known as matching pennies. So what happens with other games, and in particular with the famous prisoner's dilemma game? So here are the payoffs. Here's a version of the payoffs for that game, where in the usual narrative for the game, one interprets a red action as being defect and a green action as being cooperate. So just as we talked about before, we can imagine defining strategies for the prisoner's dilemma game based on finite state machines. So here are a few examples of iterated games between two-state machines, now with payoffs determined by the prisoner's dilemma game. So in the case of match or not, it was visually easy to tell whether a particular payoff was +1, -1, or 0, just by seeing whether the actions of the agents matched a particular step. Here it's not quite so visually obvious. But using the actual payoffs for the prisoner's dilemma game, we can compute the cumulative payoffs for examples like these particular ones here. And unlike in match or not, which is a zero-sum game, the payoffs for the two agents don't have to sum to 0 at each step. So here are the relative payoffs for each of those games for the two possible players. So much as we did before, we can consider competitions between agents whose strategies are based on all possible two-state finite state machines. For match or not, the zero-sum nature of the game makes the resulting array of payoffs symmetrical. Here, there's symmetry only from the fact that the payoffs remain the same if one interchanges the roles of agent 1 and agent 2. So these are plots of competitions between machine 1 and one machine and another machine for all the possible machines playing on the left as the mean payoffs for agent 1, on the right, the mean payoffs for agent 2. So with this setup, we can now ask what machine is the overall winner. We did that before, say in the sense that it has the largest average mean payoff playing against all other distinct two-state machines. As a result, all the payoffs are negative, but one is less negative than others. And the one that's less negative than others turns out to be machine number 30, which is this machine here. So in the literature of prisoner's dilemma, this machine is often called the grim trigger machine because it gives a strategy that starts with a green, then repeats that until its opponent first gives a red, after which it's kind of triggered to always defect and give red. So running this machine against all other two-state machines, we get the following behaviors, which corresponds to these mean payoffs. So looking at the average mean payoff for all two-state machines, the ranking of possible two-state machines is this here. So it's notable that machine 22, which corresponds to the famous tit-for-tat strategy, here's that machine, is quite far down in these rankings here, even though it's often identified as the most successful in collections of human-suggested strategies. So for our kind of enumerate all possible strategies, including strategies that don't make a lot of sense, but we're enumerating all possible ones, we get a different winner from what people have got in my opinion, somewhat arbitrary kind of games against kind of human-suggested strategies. So the rankings that we are showing here are based on average mean payoffs obtained after many iterations of the prisoner's dilemma game. But if we do only a few iterations, the rankings can be different. So here's the rankings of different machines as a function of the number of steps over which the average is taken to figure out who's the winner. So if we zoom in at the beginning, we can see that the machine 30 only starts being the winner after 13 steps. Before that, if you average over fewer than 13 steps, machine 30 doesn't look to be the winner. So machine 20 gives a constant average mean payoff of -1 that we see happening here, while machine 30 yields an average mean payoff that's given by basically it limits to -19/22 or -0.86. So that's how that machine comes to be eventually the winner, even though it takes a while to get to that point. So what about three-state machines? So here's the average mean prisoner's dilemma payoff for each of the three-state machines playing against all others. So the distribution of these average mean payoffs is this. The machines with the highest ultimate average mean payoff are these ones here. But this ordering only emerges after more than 500 steps. And we see that here. This is kind of a bigger version of the picture we saw before for two-state machines playing two-state machines. This is now three-state machines. So the crossover of average mean payoff, who's the winner as you go to more and more steps, that crossover is surprisingly complicated. And sort of the seemingly quite random variation of average mean payoff reflects the combining of many different periods in the always ultimately periodic behavior of competitions between machines. So how do three-state machines do compared to two-state machines in the prisoner's dilemma game? Running two-state machines against each other, machine 30 gets the highest average mean payoff of about -0.866. Meanwhile, for three-state machines running against each other, the highest average mean payoff achieved is a very slightly smaller -0.885. So -0.866 versus -0.885. So what about two-state machines running against three-state ones? Well, they don't do very well. Machine 30 does the best, but now it gives an average mean payoff of not -0.866, but instead about -0.97. But now, running three-state machines against two-state ones, the best average mean payoff is larger, about -0.80, as achieved by machine 2743. So the mean payoffs obtained by running this machine that I'm showing against all possible two-state machines, these are the mean payoffs achieved in those competitions. So how about four-state machines? So running all these against two-state machines, the overall winner is machine 336766 with average mean payoff of -0.77. So the mean payoffs achieved by this machine, this four-state machine, running against each possible two-state machine are these ones here. Are very similar to those for the winning three-state machine. The only different behaviors occurring when the opponents are the two-state machines 20 and 30, these ones here. So summarizing all of this, the winning machines with small numbers of states that we found for prisoner's dilemma are these ones here. But what about machines with more states that we might find by adaptive evolution? Here's an example of adaptive evolution for 10 states competing against all two-state machines. There's the loss curve, the fitness curve, building up. And we see a lot of sort of small jumps further down in this behavior. So after 1,000 steps of adaptive evolution, we get this 10-state machine with an average mean payoff of minus 0.73. So the behavior of this machine competing with all two-state machines is the following. And that's the result of adaptive evolution in this case. Let's talk about the space of all possible games. We've now looked at two specific examples of games, Match or Not and Prisoner's Dilemma, and we've seen very similar phenomena in both cases. What about other games? If we allow just payoffs -1 and +1, as we did in the Match or Not game, there are a total of 256 possible games. Those are the first ones. And of these, 16 are zero-sum, like Match or Not, in the sense that the sum of the payoffs for the two agents is always zero. And 16 are symmetric, like Prisoner's Dilemma, in the sense that the payoff for the two agents is always the same. So for each of the 256 possible games, we can compute different payoff configurations. We can compute the average mean payoffs for each possible two-state finite state machine competing with all two-state finite state machines. And that's the result. So the winning average mean payoffs for these 256 games are always -1, 0, or +1. And in most cases, many machines achieve the maximum payoff across all games. So, and this shows the kind of the number of times each, that's so odd. The well, the number of times, the number of distinct games. I think the slide is in slightly the wrong place. The number of distinct games in which different maximum payoffs are achieved. What about if we look at, so these are the payoffs, maximum payoffs that are achieved by different machines across different possible games. So let's say we're looking at games with payoffs -1, 0, or +1. There's 6, 5, 6, 1 such games. And the story is very much the same as before, with some slight differences. Yeah, so it really doesn't matter much what, I'm not quite sure what the slide is, it doesn't look quite right. Which game you use, Prisoner's Dilemma, matching pennies, whatever else, the same kinds of general behaviors seem to show up. Okay, let's talk about something different. Let's talk about cellular automaton strategies. So what we've done so far has been based on using finite state machines as our source of strategies. Now we're going to turn to another source of strategies, cellular automata. The setup we're going to use takes the actions of our agents to be determined by running cellular automaton rules. The basic idea is that at each step, the initial conditions for the cellular automaton are given by the sequence of actions taken by the opponent so far. So the next action of our agent is then determined by the value of the cell obtained by running the cellular automaton for as many steps as there were actions taken so far by the opponent. So more specifically, let's say the rules for our cellular automaton are these ones here. And let's say the actions taken by the opponent so far are these ones here. Then the idea is to run the cellular automaton with those actions as its initial condition. And the rules that I set up, they just sort of grow to the right like this. And then what we do to find the sort of what the cellular automaton strategy says to do next is to extract the final cell value at the bottom of this pattern to determine the next action to take. So for example, if our two competing cellular automata are these ones here, then the successive steps in running them against each other will be these here, where what we've done just to make these pictures is to flip around, left, right, flip the things for agent 2. So the actions that are taken on each step can now be read off either from the opponent's initial conditions or from the outer diagonals of the final pattern that's generated. So to analyze the competition between rules, we can assign payoffs, say from the match or not game. And in this case, we get the following cumulative payoffs. So this is now using Cellular Automata as generators of strategies, and we're doing the match or not game. There are altogether 16 possible Cellular Automata of rules of the kind we're using here. And running each one of these against every other, we get the following array of limiting mean payoffs. So this is now every Cellular Automaton strategy against every Cellular Automaton strategy. Well, some notable competitions in that of Cellular Automata competing with Cellular Automata are these ones here. And the cumulative match or not payoffs in these cases are these here. So we're seeing here that one cellular automaton will win for a while, then lose, then whatever, and eventually there's sort of divergence. The case of most of them, it's pretty clear who's winning pretty quickly, but for the case of Rule 6, Cellular Automaton Rule 6 against Cellular Automaton Rule 7, it's more complicated. Even after 500 steps, it's still not clear which rule will win. They keep on kind of duking it out and getting an advantage over the other. So the underlying behavior of the cellular automata that leads to this kind of outcome for payoffs looks like this. So agent 2 is quite simple in its behavior. Agent 1 is a bit more complicated. On their own, these two rules behave in rather simple ways. And in fact, Rule 7 is just directly the XOR rule. But when they're set up in competition, the effective rule that emerges, which was this thing here, has more complexity and apparently unpredictable behavior with no sign, for example, of periodicity. So looking across all the cellular automaton rules, the one with the largest average mean payoff turns out to be Rule 14. And this is its average mean payoff playing against all other possible rules. In a sense, Rule 14 finds a very simple solution, generating either constant or period 2 behavior and sort of forcing its opponent to do likewise, and in the end giving an average mean payoff of exactly -11/16 or -0.69. So what about with more complicated cellular automaton rules? What about, are the winners still ones with simple behavior? Let's look at the 3 color analogs of our cellular automaton rules. There are 3 to the 3 to the 2, or 19,683 of these. And in each case, we can make a decision about the next action by looking at the final value mod 2, because this is now 3 state values, and we're only taking 2 possible actions. So we're taking those states mod 2 to determine the action. So running all these rules against the 16 two-color rules, the distributions of these scores are these here. And once again, the best performing rules, such as it happens, Rule 15911, behave in rather simple ways. So looking, as we did for finite state machines, at the compressed size of patterns versus the average mean payoff in the corresponding competition, this is the result we get. We see that the highest payoff rules tend to behave in simpler ways. So the rules with the most complicated behavior, at least by this measure of compressed size, have average mean payoffs near 0. A typical example being Rule 11948, which is this is what it does against all the two-state rules. So some of the more complicated competitions in this case are things like this. Actually, there are the kind of the payoffs, the cumulative payoffs for those rules. That's what they do underneath, and those are the cumulative payoffs that they get. So what about different games with different payoffs? The underlying behavior of particular rules competing with each other will always be the same, but their payoffs will be different. And so, for example, in Prisoner's Dilemma, the cumulative payoffs for two-color rule 6 versus two-color rule 7 is now this here. Playing, whereas in the case of the payoff for match or not, this was the one that kind of kept on trying to compete with it. The two things kept on getting a lead and changing the lead. So playing each two-color rule against all others, the average mean payoffs are these ones here. So rule 13 has the highest average mean payoff of -1 and shows fairly simple behavior. Looking at the compressed size versus average mean payoff for the games between three-color and two-color rules, the phenomenon of high payoff being associated with simpler behavior seems even more marked than the prisoner's dilemma case for prisoner's dilemma than for match or not. Okay, cellular automata versus finite state machines. We've looked at finite state machines competing with finite state machines and cellular automata competing with cellular automata, but what about cellular automata competing with finite state machines? Here's an example of a particular step in a competition between a cellular automaton and a finite state machine. The cellular automaton's operation is over on the left, the finite state machine on the right. And here are the cumulative payoffs, in this case, for the match or not game. So running all 16 cellular automaton rules of this type against all two-state finite state machines, the mean payoffs are these here. So that's a finite state machine on the x-axis playing a cellular automaton rule on the y-axis, and this is the average mean payoff for the two different machines got in these cases. So averaging over all finite state machines, the mean payoffs for the possible cellular automata are these ones here. So rather boringly, the winning cellular automaton is rule 0, which just generates a green in response to any finite state, what any finite state machine does. So it's just green, green, green all the way down. So this yields an average mean payoff of only plus 0.18. But what if we use three-color cellular automata? Here are the average mean payoffs for that case, with the winning case highlighted there. So summarizing the various competitions between different types of strategies, we see that running against two-state finite state machines, the most successful competitors are by a small margin three-color cellular automata. Okay, so let's talk about adaptive evolution of cellular automaton strategies. Just as we did before for finite state machines, we can consider adaptive evolution of cellular automaton rules, which is also something that I've studied in other contexts somewhat extensively recently. Well, as a first case, let's consider adaptively evolving a four-color cellular automaton to get the best mean payoff against the most successful three-state finite state machine from before, machine 1165. At each step of adaptive evolution, we'll randomly change one of the four squared, i.e. 16 cases in the cellular automaton rule. So keeping the mutation if it gets us at least the payoff we had before. We get a typical adaptive evolution fitness curve, here it is, with the mean payoff limiting to +1, and the breakthroughs in this picture correspond to the following rules. So, as is often the case, the early breakthroughs are somewhat complicated. But in the end, the solution that emerges shows rather simple behavior, something we can see at least some evidence for in if we put the results at successive mutation steps together. So what about adapting cellular automata to compete with other cellular automata? As an example, let's use adaptive evolution to find a six-color cellular automaton with the largest average mean payoff when competing with all 16 of the two-color cellular automata that we've considered so far. So here's a typical fitness curve for this case, lots of small jumps. After 1,000 mutation steps, it's reached a rule that gives an average mean payoff of 0.91. And here's what happens when that rule competes with all of our two-color rules. So what if, as in the finite state machine cases above, both a rule and its opponent are undergoing adaptive evolution, say on alternating steps. Here's an example of the successive payoffs one gets with a pair of 4-color cellular automaton rules. And here are the corresponding actual behaviors of those rules. What are the underlying cellular automata doing? Well, here are results from a sequence of mutation steps illustrating that adaptive evolution can select both rules with very simple behavior and rules with somewhat more complex behavior. All right, let's talk about Turing machine strategies. We've looked at strategies based on finite state machines and strategies based on cellular automata. Now let's talk about strategies based on Turing machines. For our purposes, we can think of Turing machines as in some ways interpolating between finite state machines and cellular automata, though they also introduce some entirely new features. Our basic setup will be to use the opponent's actions as the initial values on a Turing machine tape, with the latest value on the right, which is where the Turing machine head is initially placed. We then run the Turing machine until its head goes further to the right than it's ever gone before, at which point we determine the next action from the value that appears at the initial head position. For example, if we consider a Turing machine that's defined by this rule, then imagine that the sequence of opponent actions is this here. Then we can run a Turing machine with that as the initial condition, and we get the following. So from this, we can read off the next move according to our Turing machine strategy, in this case, the green square just before the place where the head has gone off into its gray area on the right. So in our finite state machine and cellular automaton setups, we did just one step of evolution for each step in our game. In our Turing machine setup, at every step in our game, we're running the Turing machine for as many steps as it takes for the head to go further to the right than it started. So here's what happens if we take a particular 3-state machine and have it compete with the Turing machine that we showed before. This is what happens. And with match or not as the payoff, the cumulative mean payoffs look like this, and that means that in this case the Turing machine is winning. So there are a total of 4,096 Turing machines of the type we're talking about here, with 2 states and 2 colors. Running each of these against our sample 3-state machines, the 3-state finite state machines, the mean payoffs in the match or not game for all these Turing machines are these here. So there are several Turing machines that have limiting mean payoffs of +1. An example is machine 2259. And there's kind of a tricky issue that comes up here. Our Turing machine strategy works by running a Turing machine until its head goes further to the right than it started, so that we can consider that it halts. But what if it never halts, like a Turing machine like this, where the head is just tooling off to the left and never goes to the right? For our purposes, we're just saying that in this case, the payoff is undefined. And if such an undefined payoff ever occurs in a particular game, we assume that the mean payoff for the whole game is undefined, leaving a gap in the plot that we made before. So that was the plot, and you can see that there are gaps for machines that just didn't halt when we tried to play them in this game. So what if we have Turing machines compete against, say, all distinct 2-state finite state machines? So here's the average mean payoff for each case there, with the gaps being the machines that don't halt. The maximum value of +0.4 is achieved for Turing machine 2403, which is this machine here, which yields the following behaviors and limiting payoffs when competing with each of the 22 distinct 2-state finite state machines. So what about Turing machines competing with Turing machines? To keep things manageable, we can look at 1-state Turing machines, of which there are only 16, with 2 colors, and running each of these machines against each other, the array of mean payoffs is this is the array of average mean payoffs, where the gray parts are for machines that just don't halt. So the average mean payoff for each of these machines is given by this, and the winner among the machines, all the machines, is Turing machine 113. So running this machine, and remember this is a one-state machine, so that's why it doesn't have pointers for its head. So running this machine against all other one-state, two-color Turing machines, the behaviors we get are these ones here. So if we look at cumulative payoffs, we can see that many give mean payoffs that approach 1, although some don't, yielding in the end an average mean payoff of about 0.8 plus 0.81. So a typical competition between two-state Turing machines is what's shown here, which yields a slightly more complicated pattern of cumulative payoffs. That's what it looks like. But so what happens if two-state and one-state Turing machines compete? Here's the array of mean payoffs for all 4,096 two-state machines running against the 16 one-state machines. Two-state machines along the x-axis, one-state machines on the y-axis. The average mean payoffs for two-state machines are, well, as follows, with a maximum of about 0.81 as the maximum payoff. All right, so, well, we've now seen many examples of the Ruliology of competition. And perhaps more than anything else, it's now clear that if we look Ruliologically at all possible programs of particular types, the picture of how competition works is quite complicated, even when all the programs involved are simple. In a sense, this is a typical result of computational irreducibility. To know how competitions between programs will work out, there's basically no choice but to run them and see what happens. Sometimes the programs that win do so in very simple ways, in effect exploiting simple hacks. But in other cases, things are more complicated. Sometimes two competing programs, which both show complex behavior, but both showing complex behavior, and in a sense, it'll just so happen that one of them wins, even when they both show complex behavior, just sort of so happens that one of them wins. But sometimes the win will be more systematic. And typically this happens because the behavior effectively plugs into some pocket of computational reusability that systematically outcompetes opponents of a certain type. Well, we mostly looked at extremely simple programs, which in some sense inevitably have to expose the same rules to every competitor. But particularly if we have a fairly small collection of competitors and a sufficiently large program can in effect expose a different part of its rules for different competitors, and so have sort of a customized sub-strategy that separately wins against different possible competitors. So in looking at adaptive evolution of strategies, we've often dealt with larger programs, and we've typically seen that the adaptive evolution can be quite successful at finding winning strategies. But as is typically the case with adaptive evolution, there's no obvious way to describe the mechanism of the strategies that are produced. Instead, it's more like what we've seen in other studies of adaptive evolution. The process of adaptive evolution puts together certain lumps of irreducible computation that in our case here, in effect, just happen to be competitively successful. Different games corresponding to different patterns of payoffs lead to results that are different in detail. And if one constructs a detailed narrative about the course of a game, it may well seem different for different games. But at an overall level, there seems to be remarkable similarity between different games, and the key phenomena seem very much the same. What does this say about practical situations where there's competition between agents? One thing is that it's typically going to be difficult to predict in advance or to prove a theorem about what the best strategy will be. When there's enough computational irreducibility that that there's enough computational irreducibility involved that one will basically just have to try running different competitions and seeing what happens. In a sense, the very diversity of behavior we've seen here suggests that the idea that Ruliological investigation is critical. Finding some simple parameterization of possible strategies won't be enough to get an accurate sense of everything that can happen. There's no chance but to systematically enumerate some version of all computationally possible strategies, which is what we can do in our Ruliological investigations. And yes, what we've done here just scratches the surface of studying the Ruliology of competition. For a start, one can scale up the size of the programs and see what new phenomena occur. One can expect that mostly things will be the same, with computational irreducibility the dominant force. But there may be new and unexpected pockets of reducibility, perhaps each with their own paths to competitive success. One can also imagine investigating different kinds of computational systems that serve as meta-models appropriate for different applications. The principle of computational equivalence suggests that there'll be a certain universality to the overall results, but details will be different. And those details will potentially be important, particularly in interpreting results for very different domains. Even if what matters for ultimate purposes of competition is well captured by a finite state machine or a cellular automaton, the way one gets to those from microscopic biology or human decision-making or societal interactions or AI competition and so on may be very different. Okay, well, I had a further note in this piece, historical and personal notes. There's a long history to formal studies of games, and indeed early developments in areas like combinatorics and probability were largely driven by them. The modern field known as game theory emerged in the 1940s, concentrating on the question of optimal strategies given particular patterns of payoffs. Most often, the idea is to analyze what happens when each player makes a single move, albeit perhaps a probabilistic one, with averages taken over many instances. Particularly complete, though sometimes complicated, fairly complete, though sometimes complicated mathematical results have been derived for this kind of setup and are now, for example, implemented in Wolfram language. But what about repeated or iterated games of the kind we've been discussing here? In the early days of game theory, there was discussion about defining strategies as arbitrary mappings from histories to actions, and various rather abstract mathematical results were proved, particularly for applications in economics. But by the 1970s, there started to emerge the idea that one should model agents as having bounded rationality and corresponding to limited computational resources. And by the end of the 1970s, computer experiments were being done on competition between what amounted to simple programs. A notable example was the tournament organized by Bob Axelrod for the Prisoner's Dilemma game. In this tournament, a collection of particular programs was submitted by different individuals and run against each other. The conclusion was that the tit-for-tat strategy, that can be thought of as a finite state machine, came out best, a result from which much has been made about the value of competition and so on. I must admit that I was always suspicious of the result. It seemed very unscientific to have just looked at programs people happened to have submitted for the tournament. Why not instead systematically enumerate all possible programs and see what happens? In my own work, starting from the beginning of the 1980s, I was routinely doing this kind of thing, particularly for cellular automata. I always found the setup for game theory a little arbitrary and fiddly, and I was discovering that more than I could keep up with just investigating the behavior of individual programs without trying to have them compete with each other. Still, finally, in the mid-1990s, I did have a look at what happens with a range of different possible programs in that case, cellular automata, that were competing with each other. And I summarized the result here in a note at the end of my very big book, he says, actually, picking up a copy of the book, of the very thick book, somewhere a note very close to the end of that book is about games between programs. And that's the note there. So, in a sense, my efforts here have been kind of to fill out that footnote in New Kind of Science. I was meant to come back to this and look at it in more detail. And finally, my recent work in the Foundations of Biological Evolution made me think it was time to do it. I found out that there was some literature on using models like finite state machines as strategies for iterated games, but so far as I could tell, the kind of systematic ruliological investigation I'd imagined had never been done, which is why I recently decided it was finally the right time to do it. And that's what I did. And that's what I've just described to you here today. So that's what I had to say about rules between programs, games between programs, the ruliology of competition. So thanks. I think today we probably don't have time for any questions or comments. I think this was a rather complicated discussion, and I must say it's really something where I wanted to have this as a kind of a foundation for other kinds of things that I've thought about, and understanding a question which comes up quite often, which is how do different kinds of simple programs do when they're competing with each other? As I say, that's something for biology, for economics, for studying kind of what will happen when AIs compete with AIs and so on. This is kind of a piece of foundational ruliological science needed to try and address those kinds of questions. Well, thanks for joining me here today. And until the next time, bye for now.